Not a number. Hey, owl. Why would that happen? This is nice. But why would that happen? 0 very small is nice. Seems to be mostly correct. These two are likewise shocking. What the hell is going on here? That means they deviate a lot. I guess if the result is anything that I don't like not a number, then I want to print what is the actual value of the ox, and then we're gonna draw that so I can see what that is. It should never be negative. This can never be 0. Well, maybe both 0. That would be possible. No, it's not possible. It's never 0. Come on. Okay. Yeah. At the very least, it can't draw it. So this looks like a curve which is going to infinity and then coming back. Yeah, okay, well, maybe that's the reason then. That means that yeah, that if the velocities are parallel, then I should skip it, I guess. Let's see if I can get it to draw. If I change it a tiny little bit. So I remove this too. Can it go either way then? No, it doesn't draw anything. So let's make it a 4 then. Oh no, it seems to have drawn it. Yeah, bit of stretching energy of 10 to the power 10. So it's very, very long, bending energy as well. And probably there are, all of them have that reason. So I should skip that. If they're almost parallel, then just skip it. So how do we detect that? If they do exist, and I want that standard almost equal to, almost equal, I think, but because of the highlighting, continue. Or not standard, utils, which is obviously defined in Geolinks or likeliness. No, I'm going to use utils almost equal. I don't know if I need a header, but let's add it. I mean, the header might already be included. So that would be this function. Going to use 2 values and an absolute relative error. 10 e minus 6. It's good enough for me. So something, comma something, comma 10 e minus 6. Just a small thing, right? The absolute error. What is the absolute relative error? Whatever that is. I bet I can even make it 9. Now I think about it. Come on. Let's not overdo it. 6 is already pretty the same. And then this is going to be, for example, I could do the angle, or I can take the dot product and compare this with 0. Let's use the angle. Of either, right? Doesn't really matter. Just take this one. And now we're talking about the velocities. So v0, direction as angle, compared with the velocity at 1, dot direction as angle. Should set this to true again. No, it didn't really help. Still a shitload of other numbers. Damn it, including the first one. It didn't help at all. I did something wrong then. But what? Oh, they are opposite of each other. Oh, yeah, of course. Yeah, so I have to add pi to one of them. Hello, Kyle. So if you add pi to this value, for example, then I get the other one, I guess, right? There's a minus sign, minus. Nobody wants to do the minus here. No, still not. 3 with the minus, dot. 10389 plus pi. There's no pi on it. What is the next number? 7? I don't know. Shift is equals Oh, wait a minute. I don't know what I did. That looks like not what I wanted to do. Anyway, anyone can see that that's the case. If you add pi here, then it's just, you get that, right? Of a raw, if I add this to 0.1225, yeah, I'm convinced. So, let's add pi to, I have to add it to that. Maybe I should just add it to the negative value. That would work. Like every time. The fuck? What did just happen? Could you undo everything? God. Shut the fuck up. Plus in pi. That was better. No nonce left. I guess that 0.7 was also in that as a result of almost being parallel. So conclusion, yep, that they are the same, right? Because this is no longer printed. Wait a minute, nothing is printed. I want to see a lot of zeros. Oh, ugh. So we always continue now. Okay, but that's no. How? That doesn't make any sense at all. At all. Doesn't make any sense at all. Yeah, really. I don't think so. They're not always parallel. What a waste of time. Just to check that we never get here, because I don't see any output. Yeah. Unbelievable. They're indeed always the same. Which doesn't make any sense. All these I don't get it. These should be equal to the angles. So that's impossible. It is impossible that these two are the same inside this loop. One changes all the time, the other one is constant. This is not making any sense whatsoever. Okay, so sometimes it prints parallel, but in a lot of cases they are not parallel, which is correct. So A1 is just changing, and then for one single value it's parallel. That makes more sense, but then what happens? I mean, it's not the case that these are that there is no quadratic solution, right, for anything except almost parallel. It should give me the same output, as good as the same. That is a lot of more output than the parallel lines. It does. So yeah, wop, bleep bleep. Could put it one down even. I hope. Oh, that really cuts into it. That ain't right. That ain't right. I'm still having a lot of output, but I should have kind of the same output, because if you assume that this is the same as that, that's what I wanted to prove, then if this succeeds, the other one should almost always also succeed. Clearly it does hardly ever succeed, because only a few are left, but nevertheless, and then those few are where they are almost parallel or something. No, so even this is only, huh? I'm not running into this. They should always be parallel. Therefore, it should always print this. Otherwise, you would run into this. It does not seem to happen, however. Oh, it does, sorry. We have one alpha 1 print and then a parallel. So unless they are parallel, it's saying that there's no solution. And that only happens sometimes. Gonna make sense, I think. Okay, so the problem is that there is no quadratic solution for this construct unless the angles are such that they are almost parallel. So I'm doing something wrong. Yeah, well, okay, let's think about that. So we have this. I thought, oh no, it's not drawing that. Draw it. print them. So I thought if this is a curve, and the curve exists, and it exists for the red angle. No, this is green, sorry. It exists for the green angle. And the green angle here is actually this dotted line here, so that's the tangent here. In other words, the direction of the velocity at the v is at p0, which is v0. So the direction of v0 makes an angle with q1. And then it exits according to this tangent, so dotted line here, which makes an angle with q1, which is this size. Then I thought, then obviously, is if I swapped the P0 and P1, so let's use P2 here. I put P2 in the neighborhood of P0, so they're basically the same thing now. And then I use the angle of yeah, so this is now P1, and the P1 here is the P0 for this, for the thing that I just added here, the lower one, for Q2. And then I want to make this angle, let me think, it was green, right? So I have to drag red. Oh, I can't drag that. Wait a minute. I don't know, I have no handles here. Oh, I do have a handle here. This handle. Oh, I can't do it here. I only have one handle here. Yeah, well, okay, then forget about that. Let's just swap P0 and P1. I have to remember the angles. So I have a small angle here and a huge angle here. How do I remember that? I can remember the small angle. So I'm going to put this one where that one is, which is kind of like there, I guess. And then we put this one as the small angle. Well, there's already a solution now. But, okay, now I want to swap P0 and P1. So we put this one there. How do we do that here? And it has to move down a little bit. And that one goes where this one was. And now there is no solution, but if now I change the angles by adding pi, then we get to the opposite side. Or not. Yeah, I think it would. So this one to the opposite side would be there. And then this one to the opposite side would be... It's kind of strange though. It's definitely not what I had in mind. Okay, it seems to go there. Nothing. Okay, this is definitely not working. Nope, 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 nope. So the thing that I did have in mind was to get the same solution. Something like this, right? Just make a screenshot of the other thing. Do that. Start this fish. Do this part. And then to get the same oops, did not want to do that. The exit is there, so it should be something like this. Like that, yep. Let's be way higher. Oh wait, I can see it there. Yeah, this thing is too low. Do we have it exactly the same? Well, it's almost impossible, but it's kind of like that, I think. I'll show the original too in a second. And this one is then one and a half down. No, it should be like this. Oh, this is way too high. Oh yeah, this, like this. See, so this is the beginning of the program normally. And now I made it, I swapped P0 and P1. And then adjusted the angle such that they get the same shape again. Except now P0 is here and P1 is here. Then you see that the angle here is actually the same as that angle. Aha. The same holds for this one. The reason is that we're measuring it relative to Q1. So I was thinking, you know, I was thinking it is measuring it relative to Q1, like this point. And then I have to swap that point to the other side to get this angle. But since it measures it to the positive direction of Q1, it measures from here. So the angle is actually the same. And I guess here it holds as well, although very difficult to see. Yeah, this point is on the other side. It's now here. And then that point, so you can say we rotated this. Okay, maybe I should start here. Rotate this pi radians, so it starts there. Yeah. And then this point rotates also pi there. That's what has happened. So it's still the exact same angle, but rotated pi. That was the mistake that I made. I think I can close this. Now we understand. That means that the mistake here is that I should not use plus m pi. Just swap the two angles. Now I hope you assert, right? Yep, assertion. So remove that again. Now we get here. And then hopefully this is being printed a lot. It should never happen anymore, maybe, hopefully. That should never happen because I already exit there with the parallel. So suppress all the other debug output again. Seems that in all cases less than 10 to the power minus 14 from the looks of it. Let's add an assert for that. I'm still skipping the parallel cases, I think. Or should it work as well now? So that should work as well now. Not 100% sure, but pretty sure. And this should never happen. So let's do assert not and not a number, and not a number for the other one. Yeah, I can print it. None's still happening. Okay, I guess that is related to when they are parallel. To do this, and that should not happen. Definitely not happen. No, so a little bit. Okay, let's make it E3 then. 13, I mean. Very good. And if we don't do this, then we have nons sometimes. But yeah, it just happens. It just happens when they're parallel. Nothing we can do about that. Can do a continue here. Maybe. Let's turn it off again. Turn off before we do the continue. Hmm. No, it's not it. It did print not a number, but these are not a number. Not a number. So ESA equals minus ESB then? Oh, very unlikely. But what else could it be? I don't know. I think it's good enough. The formula is correct, right? So, yeah. Let's get rid of all of this. So swapping B0 and B1 and then swapping the angles. That's the same thing. That then also holds for the derivative. So I only have to calculate the derivative for one angle. And then I also have the derivative of the other angle if I swap, if I want negate Q1. So what I want to have is everything, right? The whole div. Right, so I want to have the partial derivative for one of the angles of both the stretching energy and the bending energy. Let me think. Might as well use the Bezier curve object to currently have quadratic stretching energy. Let's add a few private functions. A lot, actually. Man, it's getting so tired of this music. I could say the V0, which is really two variables, V0x and V0y. They have been calculated from the angles, so the quadratic form. What the hell? Oh, that was the two angles, sorry. We just passed it. Start at the top, direction, comma. This one. So let's take the derivative of just this angle. Without without looking at that yet. Then, well, I can take the derivative of this with respect to this angle. Or maybe combine it. Oh no, I cannot combine it. This is already Q1 and N1. These are two functions. I think I'm going to do the whole derivative thing manually because yeah, that was my decision today. Octave is not really helping, you know. A 100-page formula is unusable. So I think if I'm being smart, I can do it. Well, using the output of Octave is way too big. Let's split this one up into two functions. One that calculates v0x and one that calculates v0y. Which I guess I only need to calculate the derivative. So I can assume that this is already called. That is, but the Bezier curve has already been defined. And this, we already have passed this as well. Although it might be on the edge, but well, I don't think that will happen. After calling the above function, this function could be called to redo the calculation of v0 x coordinate. So mysterious, but let's not overthink it. My subconscious told me that I need it, so I'll just do it. Double Bezier curve. This is a private function. So that is v0x. And it takes the same angles. So I need to redo this if I want to calculate that. I'm going to need it. Where P1 is now I can now call the functions of that, right? So P1 returns this shit. That should be P1. And then I can do return the x coordinate of this whole thing. Maybe I should pass a Q1 and an N1 here as well, because I probably need that continuously, or am I mistaken? No, I don't. I only need it for this function. I only need the x coordinate of these two. Let's do that. So I'm just getting directly double Q1x, and that is then P1x minus P0x, which is probably way easier than P0 is this, so, and this is 0 for the quadratic, and I subtract it, so what I really need is adding these two, and then take the x coordinate of that, which I can also access directly. And N1, I mean, that is just a rotation. That's actually minus the y coordinate of Q1. So I still have to calculate that one as well. No, whatever. So this is minus the y coordinate of Q1. So that would be basically the same thing, but then with a minus and taking the y. This is the same. Everyone agrees. So Q1, no, sorry, P1 is all the coefficients added. Look at it again. 0, 1, 2, 3, all added. This is 0. We subtract P0, so we subtract that. So P1, sorry, no, Q1 is equal to that. And then just take the x coordinate. So and then also take the y coordinate. I'm going to do that like that. Yeah, totally. This has to be correct. Although, yeah, I don't know. Yeah. This is a direct copy, so that should work. And then we have that one, which is just twice the same thing. Once times the cosine times q1 plus the sine times n1. And now we turn just the x coordinate, so this should work. And then I can do the same thing for the y coordinate. Still have to fix that, but okay. This stays the same. And this is also the same, except now we need the y coordinate. Yeah. Okay, then fix this. So the y coordinate was, well, the y coordinate. And the y coordinate of the normal is the x coordinate. So that's plus the x coordinate of q. Yup. And then we can calculate, I have to calculate, I think, a0 x as well. I think I want to move this one out of the way now. So the arc length has v0x and v0y, both squared added. That is that one. Definitely needs its own function, I think. There's my comments with nice stuff. Well, here's a square. So the square of the length of v0. Can only need a0 times v0, you see, here as well. At least for this part, for the quadratic. But still, times z plus z, yeah. I think I want to express a0 and v0. Really forget about the a0. If we would do that, then this is v0, this is obviously also v0, then that would be v0, and then this is just v0, and this, well, everything. 100% depending on, well, the x and y coordinate of v0 in that case. And then I can take the derivative with respect to v0, x and y. And then multiply with the partial derivative of both with respect to alpha 0. So I do want to have an a0, but I want to see how that formula looks like expressed as v0 and constants, so like p0 and p1. So I need a Bezier curve a0x. It's not really a function anymore of those angles. Not at all. Just kill that. The other two are. Now I suspect this one is not either, or no, because I want to express it in v0, which I already have as part of my curve object. So how was A0 calculated? I think that is done in quadratic from V0. It's pretty straightforward. So this function here calls quadratic from V0 at the end. And that then initializes A0. Yeah. Yeah. It's just this. So these are constant, and then it's actually just a constant minus V0. Super easy. Times this, the whole thing times 2, because this is just a half A0. Gonna copy this. Yeah, it's a comment, so let's just use A0 like that. So this would return the X coordinates. And then here I'm using the same subscripts. Subscript 0. So I need Q1 again, and well, only the X coordinate. Q1 being P1 minus P0. But yeah, if I want to take the derivative of this, we have, of course, to realize that these are constants. But are they, right? I mean, I think Q1 is a constant. These are not, I think. But if you add them, they are. Something like that. I think this is V0. So this is something minus V0. Q1x is a constant anyway. So I have to treat it as a constant when I take a derivative. And here I explicitly write V0, even though it's also m coefficients 0 dot x. So I know that if I take the derivative, then this is my variable. Damn it. Undo, redo. What did I do? I don't know where I am. Redo. Sit. Undo. I gave it to God. Blah, 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 blah. Yep, and then we have, of course, the same thing here, but then for A. Where A0 is defined as 2 times coefficient 2. Yeah, so a coefficient 2 itself is not a constant. It depends on those angles, of course. I mean, both velocity and the acceleration change. If you change the angles, they form the shape to begin with. But this way I wrote it in terms of V0 and a constant. I'm getting filled with doubt more and more. I always have to think about this Star Trek episode where this doctor, what's his name again? McCoy, has to operate on Spock, put his brain back. So he goes under some kind of alien machine that teaches him how to move a brain into someone's skull and reconnect it. And then he can only go under the machine once. If he does it twice, then he dies. It's a bit too much of a strain. So he screams like he's tortured while he's under the machine. But then he starts his operation on the brain of Spock, and he's like, oh, it's so easy. A child could do this. So he happily starts operating. And then while he goes, he starts to forget things, It gets harder and harder, and his sweat on his forehead Well, in the beginning he thought it was super easy, and time progresses, it doesn't feel that easy anymore. And that's the same feeling I have often when I'm programming. At some point it feels easy, you start coding, and then slowly it isn't that easy anymore. So yeah, what was my next step? Maybe I should just reveal my thoughts. So my thought was, I need to take the derivative of the total energy, which means just the derivative of the stretching energy plus the derivative of the bending energy added. There's just two functions. To concentrate on one of them, concentrate on the stretching energy. The derivative of the stretching energy, well, the stretching energy equals the arc length squared. So that is simply 2 times the arc length squared times the derivative of the arc length with respect to the angle. And then I thought, well, I think that everything goes through the velocity, or well, the velocity is a vector, so we'll have to work with 2 variables. I could take the partial derivative of the arc length with respect to v0x times the partial derivative of vx with respect to the angle, I think, plus the partial derivative of the arc length with respect to v0y times the partial derivative of v0y with respect to that angle. I'm not even sure about that, but maybe we should verify that first. So now I'm trying to express this whole thing in terms of v0 and v0 in terms of the angle. That is v0x and y both. And then we can follow that route. And here it looks a bit foggy, I have to admit. Okay, that means that this whole thing needs to be clearly a function of v0. And then I mean capital V0. So v0, x and y. You can do that by expressing each and everything that is here in those variables. For example, the v02, which is used, is this, which is this. Yeah, so I have expressed that into those 2 variables. Hello, dev data. Going to remove this, which of course it's double, and I don't know. Already say it here basically. V20, that's a new one. So I'm trying to do this one manually, but then smarter, because this is a bit much. And it went on, just my scroll bar is large enough. V0 is what? The square root, yeah, I was going to look for the square root here. Sign, square root, sign, subscript. Square root, that worked last time. The square root of V02, which was this. Yeah, let's forget about square root. Well, for a moment, and then just fill in the squares. Here, this. Square root of these things squared. Yeah, not something more difficult, I think. A0 is, I bet, the square root of that, so yes. It is A0, which is the square root of that, right? Which is the square root of the square of this plus the square of this. So I can put a 2 in front of it. How does that work? 40, yeah, that's just a 2 in front of the root. Forget about 2. I'm not sure about it. I don't know. 2 squared is 4. Yeah. 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 I think that's correct. Now Z. Z in terms of V, X and V0X and V0Y. So that is, as everyone can see, V0, and of course we don't see any dot anymore. Dot A0, which is V0X times what? No. Times A0X plus V0Y times A01. That's how the dot product works. And then we fill in again what that is. A0X equals this plus that times 2 times, well, probably the same thing, but then with the Y. Which is equal to 2 times V0X times that minus V0X squared plus V0Y times that minus V0Y squared. Or now I just return the readable version. Hi Daniel, thanks man. Hey Post Bunny. Well, I have a plan doing this. The plan is to also write down, write the partial derivative functions for each of these. S, which I think is easier if I first have them all separately, even though they are like literally the same as this, but hey, the comment is going to help me. Yeah. And then version 2 looks really good. This is version 1, it's always bad, and then you do a rewrite and then it looks better, and then finally after 10 years you really understand it and you do again a rewrite, and then you publish it, and then everyone thinks, oh my god, this guy is so smart. But no, look at the first version. when the guy didn't understand anything about it at all. If you see something and it's super smart, then it's usually version 10, you know? So in the end, it's always possible to morph things into that's, well, at least with mathematics, into something that is that if you would do it the first try, the first attempt that way, then it would be super smart. Well, yeah, often it even takes, you know, certain things have taken generations before they were able to formulate it in a smart way. I'm sure that if I would work my whole life on this, then eventually I could probably invent my own mathematics or something on top of it, and then mold everything into something that is just super symmetrical, works for any number of dimensions, and, you know, like that. Well, it would take a lifetime. And the first step is always to get something that works at all. What is S? S is the square root of something. Yeah. Can't make anything better of that than this. Well, I have A02 defined. All these functions exist. So I should be happy with that, taking the square root of it. A03. It's not really used that often, I think. Maybe once. Twice. Whoa, okay. So we'll turn it into a function. Yep. Just A0 to the power 3. Maybe should define it like that. Can take the derivative of that, right? Now, how many more shall I split this up? Definitely the logarithm. Logarithm is divided by something. Just 2 times that. But we have a multiplication in front of that. Let's make this a function. And then maybe those can be combined into 1. Z times A0. Could make that a function as well. No, I have a V0 times A0. Okay, before I do this one, let me figure out if I can actually go through two partial derivatives to end up with one. I'm not even sure. Well, let's ask Gemini, just in case it has something sensible to say about that. So... a function of basically two variables, each of which are again function of one variable. Let's call that one variable x. Yeah, why not? Okay. I have two functions, f of x and g of x. And I have a function h f of x and g of x. It is too hard to write out h of x. Can I determine the partial derivative then I need a D. Was probably Greek lowercase delta, this one. dH dx Absolutely. Here is how the beauty of Umut. Hello. Okay, it has a name. Multivariable chain rule. We have a function h that depends on two intermediate functions f and g, which in turn depends on x. That's exactly what I just described. then the partial derivative of h with respect to x is just the sum, which is what I said before. Oh, I just wasn't sure. What the hell is it doing here? Bullshit. This is utter nonsense. I mean, this h, depending on u and v, is expressed in u and v. And then it's going to calculate what? I think it got confused. Maybe it meant the f and g here instead of u and v. But then we get this. Let's see, f, it's blah, blah, f and g. So f is u. The h, the u. Yeah, that is v. And then this is the h, the v, which is u plus e to the power of v. Yeah, I just got confused. After buying in general? No, just don't use u and v at all. Anyway. I feel I still have to check it. Multivariable chain rule. Let's just Google that. Chain rule multivariable functions. Well, I guess this. That's a straight D instead of a delta or a round D. Did I pick the wrong thing? Because it doesn't look completely different from what I picked. It's what it used. Yeah, I should have used this. I don't know where to find that. I'm using Arch. keep it safe. Okay, but this is the straight D. The question is if you can do the same for the partial derivative then. Yes, you can. No, you cannot. Sorry, I thought it was the other D. Ah, here we are. Yeah, okay. So my G and F are X and Y here. And Z is H and U is X. But then it works. So the one that are two variables. I've kind of only want to talk about one variable, but I have two variables because I have many variables actually. But U and V could be the two angles. In the end, I'm going to have many of these variables, right? All the angles. Yeah. You know, I definitely have a partial derivative for each angle. If I have a whole spline of things and every angle, the angle of the tangent at every point is a different variable. And then take the partial derivative of the energy, total energy, with respect to each of the angles. And then we have to sum all of them up. Which would be that sum, I guess. No, wait. No, I have to sum that with that one then. Anyway, Jimmy was right. And we can apply the chain rule here. So I need calculate the partial derivative of each of these variables with respect to v0x and v0y. And then multiply that with the partial derivative of v0x and y respectively with respect to alpha 0, and then add everything up, something like that. I'm going to treat, or already treated ZA0 and everything as a function. So I wanted to make more functions. Or do I? So do the partial derivative of this with respect to hell of a difficult still. I think I need to really split it up way more. I could start from the bottom now, so then work my way backwards. So I'm just going to make a function that returns, I don't know, just something that looks like it makes the formula easier. In other words, this, for example. And that thing then needs a name. But hey, I have an idea. ZA0 plus A03 divided by S. Looks like a good function name to me. Zap. What the fuck do I still up? It's way late, man. I have to go to bed. Yeah. I'll continue this tomorrow. Good night, everyone. Nobody warned me that it was